Hello and welcome. In this chapter, we'll be covering an introduction to wireless communication networks. And the first thing you really need to know about wireless communication networks is that they've been around actually for a long time. So, since the late 1800s, the first transatlantic telegraph signals were sent across the ocean, obviously, by a gentleman by the name of Guglielmo Marconi. So he invented the wireless telegraph and he encoded alphanumeric characters in analog signals. The next really big thing on the radar for wireless communications was SATCOM, or satellite communications, which was launched in the 1960s. And then there were significant advances in wireless technology over the years in terms of radio, television, mobile telephone, mobile data, and communication satellites. And more recently, wireless has become a part of our everyday lives. We all have, some sort of a smartphone these days. And wireless networking is becoming more and more prevalent as we move from 4G toward 5G. We see Internet of Things where everything is networked, from your car to your alarm clock to your coffee maker, and even lots of networked sensor networks that are deployed just around various geographical regions, monitoring weather types of patterns, etc. So wireless communications becomes very important. We're living in the information age. I should also note that the father of information theory is actually one by the name of Claude Shannon, who wrote a paper in 1948 called A Mathematical Theory of Communication. And this really was foundational and visionary, and really he envisioned what we have today in terms of lots of data being transported over communication networks. So the cell phone, it started as a replacement to the wired telephone, and early generations offered voice and limited data in the 1G first generation of cell phone. And then we moved to 2G, which incorporated more digital communications. And now we're living, well, we've already been through third, and we're on the tail end of 4G technology, moving into 5G. So 4G, we know we have various apps. We have voice. We can do voice over IP because LTE is a IP enabled network. Voice texting, social networking, online shopping, obviously, mobile commerce, and video streaming, etc. So these things are very familiar to all of us in the current day. So this course will explore some of the more foundational concepts behind how we got to where we are in the current day. So the wireless impact really is profound. It makes the world smaller in a sense because everything's interconnected. You can easily, if you have family overseas, or if you're you could easily Skype with somebody from Australia or India or China or Europe. So it's really made the world a lot smaller, in air quotes, because we can just interface so seamlessly with people around the world. Um, it, you know, these systems are always on and operating. You're always connected in the current day. It really changes the way people communicate in terms of social networking. And there's a converged global wireless network that we've really seen over the years. This just gives you a little bit of the history from 1930 onward to the current day. So on the y-axis, you have the various, frequency bands. The way they break it up is in factors of 10, starting with, say, 3 megahertz. So 3 to 30 megahertz would be high frequency HF. 30 to 300 is very high frequency, and then you have ultra high frequency, then super high frequency, extremely high frequency, and they ran out of adjectives. And then from 300 gig to 3 terahertz is considered infrared. It should also be noted that the extremely high frequency has been retermed more recently the millimeter wave band, because the wavelengths of the electromagnetic radiation in those bands is on the order of millimeters in length. So we see from all the way from what's known as Safford wave radio all up through black and white TV in the 50s, followed shortly thereafter by FM radio, which operated in VHF bands, to color TV, which was kind of a crossover between VHF, UHF. Some of the other things to point out, you see cordless phones operating there in the 80s in the UHF bands, Wi-Fi, operates in what's known as the industrial, scientific, and medical bands, ISM bands, which are unlicensed, and that came about in the 90s. And then some of the shortwave protocols like Zigbee we've seen over the years, and then through 3G, 4G, millimeter wave, as you can see up here, and then moving toward 5G. So there's also some outliers. There's some of the optical communication satellites, which uses almost like light to convey information, which falls a little bit outside the realm of conventional radio frequencies, and infrared as well. So those are some of the milestones. So there's been a huge amount of growth. There's been an explosion of growth. So we went from 11 million users in 1990 to over 7 billion today, which is highly significant. So mobile devices are convenient. They're location aware. They're aware of context a lot of times of like whether it's location or what apps you're using, and it's the only economical form of communication in some places. So just zooming through here from all the way from 1G, started out analog. The bandwidth became very congested, even with just hundreds and bordering 1,000 of users. But so very quickly we realized we had to move toward a digital network for these cellular networks in order to make more efficient use of the bandwidth. So 2G really focused on making wireless cellular networks more efficient and served mostly voice at moderate data rates. 3G got even more efficient and had packet networks, which we'll cover more in subsequent chapters. And then it was based on CDMA, Code Division Multiple Access 2000, and also Universal Mobile Phone Service, or UMTS. 4G made the wireless communications even more efficient by moving toward OFDM, which is orthogonal frequency division multiplexing. Again, we'll cover that more in Chapter 5. But it's a multi-carrier approach, which allows for higher spectral efficiency. Each mobile user could get upwards of tens to hundreds of megabits per second, and for high mobility, meaning they're moving fast and often, and then up to 1 gigabit per second for low mobility access. So long-term evolution is the basically LTE and LTE Advanced, and then we've seen LTE Advanced Pro, and these are just different instantiations of 4G that added additional capability. So we've seen the mobile device revolution, not only in terms of personal use, but now it seems like we're moving more and more toward everything being networked. So originally it was just mobile phones, but today's devices, you have multi-megabit internet access, mobile applications, high megapixel digital cameras right on your phone, and access to multiple networks, whether it be Wi-Fi or Bluetooth in your vehicles or what have you, or Bluetooth speakers, or 3G and 4G networks. And the phones also have multiple onboard sensors. So this is just some of the networks that your mobile phone can access. And it's key to how many people interact with the world around them. So the mobile device revolution has required and brought about a better use of spectrum, decreased costs, limited displays and input capabilities, as well as tablets and or devices that provide a balance between smartphones and PCs. So a lot of times you see sent from my iPad or sent from my iPhone, or these types of devices where they're actually augmenting what traditionally would have been done on a personal computer. And then you have a long distance 3G and 4G, For local areas, you have more Wi-Fi based network access, and then for short distances, like in a car, etc., you see mostly Bluetooth, but you'll see later on the course that Bluetooth and Zigbee are related protocols, but one kind of stemmed out of the other. Zigbee is kind of on the order of hundreds of meters, whereas Bluetooth is maybe tens of meters. You can think of it that way for the time being. Future trends. So LTE Advanced, LTE Advanced Pro, and Gigabit Wi-Fi are now being deployed. A lot with 5G, we're seeing more machine-to-machine type of communications. Sometimes it's called device-to-device, where devices can interface directly with each other rather than having a link in between from a base station, which is traditionally how it's done. And devices can interact with each other. Whether you're talking for various use cases or industries like healthcare, disaster recovery, energy savings, security and surveillance, etc. We see a lot of this in education, manufacturing, and other areas as well. Information dissemination. So we live in a data-rich world now, where there's a lot of data being collected. So you can do data mining, decision support. Now we're seeing techniques using artificial intelligence and machine learning come about, where you can apply neural networks and deep reinforcement learning to analyze data and get to decisions in a more optimal fashion than having a human in the loop. So you kind of like they call that man-machine teaming, but more reliance on these sophisticated algorithms. Then you have automated adaptation controls, so you have smart homes, smart cities even, so home sensors can collaborate with home appliances, and even your smart thermostat and your HVAC systems can be networked, your lighting systems, your electrical vehicle charging stations and utility companies, that all of these can be networked now based on the advances in wireless communication. And basically, these devices could eventually interact in their own forms of social networking, similar to how humans do it today. Whether it be Facebook, Instagram, Snapchat, whatever the app, the machines could actually communicate with each other to compare information and make decisions based on other devices in the network. So machine to machine communication, M to M, there's going to be a 100-fold increase in the number of devices that are networked. The types of communication would involve many short messages. This is equivalent to the Internet of Things, by the way. Machine to machine and the Internet of Things are kind of synonymous phrases. And then control applications will have a real-time delay requirement, and it's much more stringent than for human interaction. So future networks, so we're in the year 2020, so we've already seen a huge increase in the amount of data traffic. So 5G is currently being defined, and there are various deployments. The 3GPP, third generation partnership project, is the standards body that is setting the standards and the vision for 5G and all the enabling technologies that go into it. And yes, that about every 10 years there's a new generation of wireless. So you can figure 2010, 4G was coming online. 2020, here we are, and into the 2020s, we'll see 5G rolling out. 2030, you'll see 6G technologies, and that's yet to be fully defined, but it's envisioned. So some of the enabling technologies for 5G include network densification. So you could think of this as like in a city where every lamp post and every garbage can is now a little mini base station called a G node B, and there can be more high data rate coverage in these small cells, augmented by the macro cells that we've seen in 4G. Device-centric architecture, so focus on what device needs, and then utilizing antennas in a smart fashion, so massive multiple input multiple output, or MIMO, to get tens of hundreds of antennas in an array where you can steer the beams toward the intended devices to give them the coverage they need. There's also millimeter wave technology ranging from 30 gig to 300 gigahertz bands, where there's a lot of available bandwidth to tap into in those bands. but it requires more transmit power since there's high attenuation at those frequencies. Not only over the air, but also obstructions affect higher frequencies differently than they affect lower frequency electromagnetic radiation. There's also native support for machine-to-machine communication. There's sustained low data rates, a massive number of devices, and very low delays. So wireless, some of the downsides of wireless, it's convenient, less expensive, but it's obviously not perfect. There's limitations with, the politics. Can you get the right policies in place for certain devices to gain access to certain spectrum? And spectrum is a precious resource, right? So these companies known as the carriers that service, that maintain the base stations and service, whether it's Verizon, AT&T, etc., they pay really good money for the devices that they serve to gain access to the spectrum. Just for example, there's Advanced Wireless Systems auction back in 2014, where it was approximately $44 billion spectrum sell-off, and this was only for on the order of 25 megahertz worth of spectrum. So it's a very precious commodity. There can be technical challenges that emerge. There definitely, besides the political, there are definitely challenges that arise just because of the physical limitations of how electromagnetic waves propagate over the air. Line of sight is typically best, but not always feasible. And it's not required because there can be reflections that bounce off various, whether it's the Earth or the ionosphere, or whether it's various obstructions. Signals can reach, point B when sent from point A, so they transmit over the channel to the receiver. Sometimes waves, depending on the frequency, can go through objects. It can reflect off objects or ground or ionosphere. There can be scattering or diffraction around edges of objects. So we'll go more into these different modes of wireless communication in a subsequent chapter. Once again, reflections can cause multiple copies of the signal to arrive at different times. This creates a multipath where the basically later copies of a signal, it can interfere with the data and distort it. So this is called intersignal interference, and it's based on multipath. Noise is just any unwanted signal in a transmission. That's typically affects the receiver, but there is external or atmospheric noise and internal or noise at the receiver, which a lot of the times is just caused by heat, because there can be thermal noise or additive white Gaussian noise or Johnson noise, which are all the same thing, which is noise at the receiver induced by just the heating of the electronics themselves. There's also interference from other users, crosstalk, as they say, Doppler spread caused by movement, which can cause, especially for multipath or multiple. It essentially causes inter-carrier interferences for multi-carrier modulation schemes such as OFDM, and I'll get more into that. So just in terms of how do you combat some of these problems, you have a lot of different things you need to look at in a wireless communication system. We'll get deeper into these as the course rolls on. But there's modulation. So modulation is just basically embedding information on some sort of carrier wave. So you may have a 1 megahertz carrier wave, and you have to embed ones and zeros on that carrier wave to be sent over the channel. There's also what error control coding you use, or so you can add extra bits so errors can be detected and corrected. There's also adaptive modulation encoding, where you dynamically adjust the modulation encoding scheme to correct to the current channel conditions. Equalization is another method that can be used to counteract the multiple effects of the channel. MIMO, using multiple antennas to point signals strongly in certain directions or send parallel streams of data. There are multiple modes of MIMO. Again, we'll get deeper into all these concepts throughout the course. Then there's direct sequence spread spectrum, DSSS, which just expands the signal bandwidth to combat some of the effects, the negative effects that are faced. Then there's OFDM, orthogonal frequency division multiplexing, which breaks the signal into many lower rate streams and can combat some of the multipath problems. Obviously, there's the political difficulties between companies. They compete for spectrum a lot of the times. So some areas have well agreed upon standards like Wi-Fi and LTE, but it's not true for IoT or Internet of Things or machine-to-machine type technologies. There's also regulations with regard to spectrum, so the governments must dictate how spectrum is used, and there's many different types of uses and users, so there's a heterogeneous web of authorities and devices that are faced with regard to wireless communications. Some frequencies have restrictive bandwidths and power levels, while others might have more bandwidth available. So this is just an outline of the text, which is what we'll follow. Part one, there's mostly data and packet communications. We'll get into TCP/IP and data networks. Then we're gonna get into wireless communication technology and all the specifics, and then we'll get into some of the specifics behind shortwave or short range communication protocols like 802.11 and 802.15, which is Bluetooth, Internet of Things, and Zigbee. And then part four, we'll get into some of the specifics of wireless mobile networks and applications. All right, so this is just the kind of a block diagram of how we'll proceed through the course. I think you'll find it to be very enjoyable. Some of the PowerPoints do have some animations which are helpful, and I'll try to go through some of these as the course progresses. This is just an example of a base station handoff, so and there is some hysteresis built in here. But basically, if you were to go into the PowerPoint and click on this, it would show you a nice animation as a car drives from base station A to base station B and how that soft handoff occurs. Basically, for the user equipment that's inside the car, it would basically there's a threshold, but then the coverage would come from base station A until it reaches a certain point, and then it would hand off to base station B. All right, so that's it for this lecture, and look forward to the course with you.